Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show CFD heterogeneous fluid mixing through a special type of heat exchanger using ANSYS Fluent fault tolerant meshing. Let us start Fluent Launcher. Initially we have to start with Fluent fault tolerant meshing, and then we need to import that CAD model from here. Let us import that model. The model is already saved as FM database with the extension of FMD. Let us open this one. Let us load it. Let us copy settings of child objects, and next to that we can create meshing objects. Meshing operation is being initiated. This is the model. For better understanding, we can have a segmented view of this model. Let us cut it from front end. From this opening, we will be providing hot water at a temperature of 100 degrees centigrade, and from this opening, we will be providing carbon tetrachloride at a lower temperature, and it will be forced at a high velocity as it will be passing through these small openings. And at this location, heterogeneous fluid mixing will be there. Initially, this container will be filled up with air, and from right hand side, from this opening, we will be providing water at 100 degrees centigrade. And from this opening, we will be providing carbon tetrachloride at a lower temperature of 10 degrees centigrade, and it will be passing through these small openings with high velocities, and it will be mixed at this location. And finally, at the right hand side, you can see that location. Right hand side here itself, it will be coming out, so it will be collected at this location. So it is a special type of problem. In this case, we will be considering heterogeneous fluid mixing of water, air, and also carbon tetrachloride. And by the same time, we'll be saying it is a heat exchanger problem also, because both entries will be having different temperatures and it will be mixed inside the chamber, where heterogeneous fluid mixing will be occurring with air, water, and carbon tetrachloride. And finally, at the exit location, we'll be having the mixture at a specific temperature. Our task will be to find out temperature at the exit location. By the same time, we'll find out temperature, pressure, and velocity distribution at different planes. Okay, so without wasting time, let us start this one. First of all, we have to show that what type of analysis it is. It is definitely an internal analysis. So we have to define that type of analysis. It is internal. We should check in internal flow through the object, and other options we can see. Definitely cap should be created, and we need to have local refinement. In this case, we are having very small openings at the junction of hot and cold water, so we need to have local refinement. So this should be checked in. At the same time, you can see other things like, from advanced options, we can see what are the things available. Identify regions, it is needed, and leakages, if it is there, that should be closed. Definitely true. So with the other default things, we can move on to the next step. So describe the geometry and flow. Next to that, I'm going to create some caps at the exit locations. So 3 caps to be provided at 2 different entries and at the exit also. Entry 1 is actually hot water entry, and its zone type will be definitely velocity inlet or mass flow rate. Let us define this one as velocity inlet, and cap name you can provide is cap 1. Let us create that cap at the hot opening. It is capped. Next to that, I'm gonna provide a cap at the cold opening, so we can define that location. It is entry 2, and definitely zone type should be velocity inlet, and we are naming that cap as cold cap. Let us create that cap at the cold opening. It is created. Let us see that one. You see here cap is created. Next to that, we have to provide another cap at the exit location also. Let us select exit location, and the zone type should be definitely pressure outlet, as it is the exit, and the name of that cap should be outlet cap. Let us create that cap. So all the 3 caps have been defined. Next to that, we have to create local refinement. For local refinement, we have to identify that region. Let's cut that model from specific plane and select that location where we need to have local refinement. You can select that region for local refinement. Region is selected. Let us create local refinement regions. It is done. Next to that, we have to identify regions. That means we have to define fluid domains. It is actually in a single space we are having 3 different fluids. Air will be there inside at the beginning, and from 2 different entries we'll be providing hot water and cold carbon tetrachloride, right? Actually, we are having single fluid domain. In that single fluid domain, we have to mix 3 different fluids. It will be a heterogeneous mixing, right? So we have to define that fluid region or fluid domain. We can define that fluid domain with the different options like centroid of the objects, or by offset method, or by numerical inputs. Offset method is the easiest one. Let us define this one with offset method. We have to show the region where fluid will be mixed. Let us provide hot cap end, and zone type will be definitely fluid zone, and this region you have to identify. That means this shape should be moved a little bit of inside to indicate the internal zone. That can be done using the displacement of x in the negative direction. Let us put x equal to minus 50. So this is indicating the domain of hot water. Let us identify that region. Next to that, we have to identify domain of cold carbon tetrachloride. It can be done using the same method like offset method. You can select cold cap opening, and that diamond shape should be moved a little bit of inside to indicate the domain of cold carbon tetrachloride. That can be done using offset of x in the positive direction of x. Let us take x equal to 50. Is fine. This is defining the location of cold carbon tetrachloride. Let us identify the region. Done. Next to that, we have to identify one void region. This is needed to restrict the movement of fluid from inside to outside. So this domain should be void. Let us provide that whole object. This void domain should be outside this region, so that to be changed with the offset method. You can move y by 50 millimeter and x by minus 30 millimeter. It is done. That means we are defining the void zone. It is identified. We have defined three defined zones, that is hot water zone, cold carbon tetrachloride zone, and also void zone. Excluding that one, a solid domain will be created by default. That is the boundary of this object. Next, we have to define leakage threshold. We like to close if any leakage is there, that will be closed. And we have to identify the leakage location. Let us identify the region as cold fluid region. Define leakage threshold. Maximum leakage size we are considering as 6.4. It is done. We have to update the region space. You can see we have got fluid region 1, fluid region 2, simplified exhaust systems, and also void region. That is 4 different regions have been created. By default, this simplified exhaust system has been created, that is known as solid region. It is showing here void, but it should be definitely solid one. This is the whole model, and fluid region 1 is known as hot region and fluid region 2 is cold region. Right? Now, while meshing these things, we have to depend on different types of machines. In this case, what we'll do is we'll be considering the best one, that is polyhexacore mesh for all the different regions. Let us identify polyhexacore mesh for cold region. It will be polyhexacore. Again, for solid region also it will be polyhexacore mesh. You can see we have identified 3 different meshing for different zones, and for void region we don't require any kind of meshing, as it is outside this region. It is needed for external analysis. Okay, so let us update these regions with the default mesh control options. We should move on. Next to that, we have to generate surface mesh, and we're considering surface mesh target skewness is 0.8, and with advanced options we'll be considering separate contact phase. It will be yes, and global minimum we're considering default as 3.2. Let us generate surface mesh. Surface mesh is generated. Next to that, we have to update the boundaries. You can see here different boundaries have been created. We're having cold cap entries, entry 1, entry 2, exit. We're having 2 velocity inlets and 1 pressure inlet. Excluding that, we're having different walls. Through these walls, it will be transferred by the way of convection. Let us update these boundaries. Let us decrease the numbers of boundary layers as 2. Add boundary layers. Finally, we need to generate volume mesh with the quality improvement limit of 0.04. Let us generate volume mesh. You can see volume mesh is generated. Let us see the overall summary. Quality less than 0.1 is 0, and quality less than 0.04 is also 0. Minimum quality is 0.178, and cell count is 67,923. Is fine. Two boundary layers have been created also, as mentioned in the pre-processing. Next to that, I'm going to switch into solution mode. Before that, we need to ensure that mesh quality is perfect. In solution mode, first of all, we have to check the units. Here in this case, the length should be in millimeter. And as it is a heat transfer problem, so definitely temperature will be considering as degrees Celsius. It's not a heat transfer problem, it is a combined problem of heat transfer. By the same time, it is a heterogeneous fluid mixing also. Let us close it. And it will be a transient analysis. It is dependent on time. We'll be considering gravity also. The direction of gravity will be y, as indicated by the arrow, this green arrow. It will be minus y. So along y direction, gravity will be minus 9.81 meter per second square. Done. Before going to models, we can see the materials. We can come back to models later on. Initially, you have to select different materials. Air is already there by default. We need to select two different fluids like water and carbon tetrachloride. That can be obtained from Fluent database. Let us open it. Fluent database. You can select water as the secondary liquid. Primary fluid will be air, that will be inside this container from the beginning itself. Let us copy, and we need to have another liquid, that is carbon tetrachloride. Let us copy and close. We have selected carbon tetrachloride, water and air as the fluid for this mixture, and solid you have to provide copper. By default it is aluminum. We need to change it to copper. Let us change it. Copy, close. We have provided copper also. Three different fluids, and the solid material will be copper. Materials have already been defined. Next to that, we need to move on to models, and from here we have to select multi-phase model should be on. We're considering homogeneous models of volume of fluid. It is not heterogeneous. So we're considering VOF, homogeneous models of volume of fluid, and numbers of phases will be 3. We're considering implicit body force. That means we have to consider gravitational force and also surface tension. Let us apply. Next to that, we can move on to phases. We're having 3 phases. Primary phase is made up of air. That means inside that container, initially there will be air only. You can rename this one as air. Let us apply. Second phase, That is the secondary one. It will be made up of water at high temperature. Let us rename this phase as water. Apply. And finally, we need to select the third phase. That means it will be made up of carbon tetrachloride, and we can rename this one as CCl4. Let us apply. Next to that, we can move on to phase interaction. Here we need to apply our surface tension values. And from addition options, we need to select wall additions that will provide smoother boundary layers. Let us select surface tension values of air and water as constant, and at random we are keeping this value of surface tension of air and water as 0.01. Apply. Next to that, second one, air and carbon tetrachloride. Let us provide the value of this one as 0.02. Apply. And the third one, water and carbon tetrachloride. Let us apply this one to be 0.05. Apply and close. Materials have already been defined, and you can see here like the viscous model should be K omega SST. For multiphase fluid mixing, this is better option. So we need to select K omega to SST model for multiphase fluid mixing operation. Next to that, we need to apply boundary conditions. Let us provide inlet velocity of hot water to be 0.01 meter per second. And temperature of this one should be 100 degrees centigrade. Let us apply and close. Next to that, we have to select the volume fraction of this inlet one. From this opening, we will be providing only water. So volume fraction of carbon tetrachloride will be 0. Apply, close, and that of water will be 1. That means from this opening, we will be providing only water at high temperature. Volume fraction of water will be 1. Apply, close, and by default inside that container air will be there from the beginning itself. Next one, that is velocity inlet 2, that means the opening of carbon tetrachloride entry. Let us provide the velocity of this inlet to be 0.1 meter per second. It will be moving with a high speed, 0.1 meter per second. This is 10 times more than compared to that hot water, and temperature of this one will be providing 10 degrees centigrade. Apply and close, and we need to assure that here in this case from this opening carbon tetrachloride concentration should be 100%. So volume fraction of carbon tetrachloride will be 1 and that of water will be 0. Let us confirm that one. This volume fraction of carbon tetrachloride should be 1. apply and close, and that water should be 0. Apply and close, done. Then outlet, that means where mixture of hot water and cold carbon tetrachloride will be coming out, that one will be having atmospheric conditions. That means in that location gauge pressure should be 0. Let us apply and close. Here in this case, from the walls heat transfer will take place by convection. We have to provide convective heat transfer coefficient at a specific rate from the walls. Let us consider the walls. We are having 6 numbers of walls. In each cases, we have to provide convective heat transfer coefficient at a specific rate. It will be convection and the material should be made up of copper. And we are considering convective heat transfer coefficient would be 50 watt per meter square degree Kelvin at a temperature of 40 degrees centigrade. And wall thickness we are considering 0.01 millimeter. Apply and close. Exactly same way you have to apply similar boundary conditions for all the walls. Let us apply one by one. All the boundary conditions have been applied properly. Next to that, we need to select solution methods. From solution methods, we'll be considering PISO method, and for skewness, we're considering Green-Gauss node-based method, and others will be considering as quick. Let us run calculations. We'll be considering 50 numbers of steps with a time step of 0.01 seconds. Let us calculate. Let us see our results from here. Initially, we'll see dynamics of flow particles from path lines. Insert new path lines. Initially, we'll see velocity distribution in the form of different particles. It will be moving throughout this heat exchanger. Let us display. This is showing velocity distribution. At the entry level, velocity is very high. It is indicated by yellow color, which is in the range of 0.4 to 0.5 meter per second. and at the exit level also it is the same level, but in the entry level velocity is little bit of high, which is indicated by yellow and red color. Next path line will be regarding our dynamics of flow particles with temperature. We're going to see particle variables as temperature, and separately you can find out the temperature of carbon tetrachloride, water or air, or even you can see the mixture also. Initially we see temperature distribution through dynamics of flow particles through this heat exchanger, right? Let us display. You can see here like at the entry level temperature is 100 degrees centigrade, and at the exit level you can see the temperature distribution, it is in a range of 37 to 46 degrees centigrade, which is indicated by blue color. And the section where hot and cold fluid is being mixed, at this location temperature is in the range of 52 degrees centigrade. Let us view these things in the form of dynamics of flow particles. Let us pulse it. It is showing the mixing of different fluids. From right hand side hot water is coming, and from top entry we are forcing carbon tetrachloride, and that is being mixed at this location, and finally it is coming at the exit. And at the exit location temperature is in the range of 40 to 50 degrees centigrade, which is indicated by color. Okay, let us stop it. You can see some other things like pressure distribution inside this one in the form of flow particles. Let us see pressure distribution in the form of flow particles. We cannot see that much of changes in pressure inside this container. Initially at the entry level pressure is a little bit high, and throughout this one the pressure is almost constant. Next one, we'll see this dynamics of flow particles for water particles only. We're going to see temperature distribution, and instead of mixture we're going to see for water particles. This is showing temperature of water, which is very high because initially we provided water from right hand side at a temperature of 100 degrees centigrade. At the junction where we are mixing hot water and cold carbon tetrachloride, at that location temperature is little bit less, which is in the range of 40 to 50 degrees centigrade, right? Next one, what you will do is when you see different contours through a specific plane, let us make a plane surface on XY, and we want to see the contours of pressure, temperature, etc. along that front plane, right? So contours, new contour, and we want to see temperature distribution through this front plane. Temperature of mixture, we want to see, you can see separately temperature of these different flow particles. It may be for water, it may be for air, or it may be for carbon tetrachlorides. We can see different temperatures for all these things, right? Initially, we'll see temperature distribution through the front plane for the complete mixture. Okay, the plane is 9. Through plane 9, we'll see temperature distribution. Let us display. This is temperature distribution throughout the front plane. So it is showing throughout the front plane temperature is very high, which is in the range of 80 to 90 degrees centigrade, and at the entry of cold carbon tetrachloride, its temperature is very less. It is in the range of 10 degrees centigrade, and as it is approaching towards the entry of this junction where the two fluids are being mixed, at that location temperature is in the range of 45 to 50 degrees centigrade, right? Next one, we'll see pressure distribution through this same plane. Let us see pressure distribution through plane number 9. You can see pressure distribution is not that much of variable. It is almost constant throughout this front plane. Next to that, we'll see velocity distribution through this front plane. Save and display. Velocity, you can see at the entry of hot water, velocity is very high, and other places it is almost constant, right? Next to that, we're going to see mesh distribution. You're going to see nodes and edges throughout all the container. We're going to see mesh distribution. Let us display. This is mesh distribution. You can see polyhex core mesh is generated. Next to that, we want to see a scene between this mesh and these contours of temperature. Let us make the transparency of the mesh to, and let us display. So this is all about our today's analysis. It is a very simple analysis in which we have conducted a homogeneous fluid mixing of 3 different fluids inside a special type of heat exchanger using ANSYS Fluent fault tolerant machine. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.